Now let's use the logarithmic power rule to solve some exponential equations. This is probably the most common technique for solving exponential equations, especially in fields outside of mathematics. So if you're going to use exponential equations in, say, finance or biology, this is probably the approach you'll see your instructor take. It's all based on Rule 3, the power rule, which said if we have a logarithmic expression, then it can be rewritten this way, where the exponent becomes a factor. Now the way we use this is, for instance, if we're trying to solve an equation where our base is a 2, we can't just take ln or log of both of the expressions and simplify, because the base is a 2, not a 10, not an e. So a common idea is to take the natural log of both sides, and then using the power rule, this variable becomes a factor. That is, we have x multiplied to ln2. Now ln2 is just a number, so we can divide both sides by ln2 and reduce. That would leave x on the left and ln7 divided by ln2 on the right, which is our answer, because ln7 divided by ln2 is simply a number. Here's one for you to try. Please don't use the technique until you have isolated the variable term. For this one, I would add 1 to both expressions. Then I would take the natural log of both sides. The t now comes down as a factor multiplied to ln2. Again, I divide by the number ln2, reduce on the left, and I've got my final answer. Try this one. After taking the log of both sides, I could do that right away because the variable exponent term is already isolated. Then the exponent t minus 2 will come down as a factor. I've put it in parentheses here to remind myself I'm multiplying it to ln5. Now you could distribute here, but we don't because it would only slow us down. Instead, I would now just simply divide by ln5. And then these two factors will go, leaving a t minus 2. After adding 2 to both expressions, I have my final answer. There isn't a way to simplify this. These are unlike terms, and so the sum is as good as it's going to get. Try this one. Now, keeping in mind that I have to isolate the variable term before I start taking the log of both sides, I would first subtract 20 and then multiply by 3, and now take the natural log of both expressions. The exponent 2x now comes down as a factor, and again I'll often do something like this to remind myself that this is a product. I can divide by ln6 and reduce, and finally divide by 2. Dividing the right-hand side by 2 means the same as multiplying by a half. Just like over here, if I multiply 2 by a half, I get 1x. The point being that the factor of 2 will be multiplied to ln6. Now this is a fine answer. I just want to make a point that it can be the case sometimes that when you look at the answer in the book, it'll look a little different. In this case, for instance, this 2 can be rewritten as the exponent for the base of 6, and then I would get ln 12 over ln 36. They're the equivalent. It's just sometimes people prefer this form. And here's the last one. After subtracting 90 and taking the natural log of both expressions, the exponent k minus 1 comes down as a factor. I divide both expressions by the natural log of 4 and then reduce on the left. And finally, I would add 1. Well, that concludes our work where we've used the logarithmic power rule to solve exponential equations.